to reduce the Cauchy problem for a PDE to a stochastic problem, then to study this new stochastic problem, and finally to prove that after the solution of this stochastic problem, I can have a solution to an original Cauchy problem. So the Cauchy problem which are of main interest in this talk are the Cauchy problem for fully nonlinear parabolic equations. In fact, certainly first I will start with a more simple case. I will consider a semi-linear case, and for this one and for the general case, I would like to discuss the construction of both classical solution and a viscous solution on a small interval. And for the quasi-linear case, which where this function f will depend on, okay, it's not should be f1 xup multiplied by q. So in this case, we will discuss the construction of weak solution or generalized solution to corresponding Cauchy problem. So let me mention that stochastic representations for solutions of semi-linear PDEs could be described like this. So suppose that we are considering this Cauchy problem, and to construct a strong solution for this Cauchy problem, we, as it was mentioned, we are going to reduce it to some stochastic problem. The simplest stochastic problem will look like this. Certainly, our coefficients could depend on x, on f, and later they will depend on higher derivative, but now, for simplicity, we consider such a case. And then we consider the stochastic process with coefficients depending on this unknown function. Nevertheless, we don't want to use the solution of a parabolic equation, and we need to add to this stochastic equation a relation which makes this system to be closed. So the relation looks like this, and in fact, in a linear case, it would be simply the representation of the solution of the Cauchy problem for the corresponding linear equation. In nonlinear case, we are dealing with a closed system, and we have to study it, probably to construct the solution for this system. Okay, here I believe that obvious that W here is a Wiener process, and under some conditions we will study this this system. Okay, this approach goes really to in ideas to the first papers by McCain and Freidlin, and then it was developed in the papers by Yuri Lvovich Daletsky and me myself. And if we are going to deal, certainly our stochastic construction will depend on the problem which we are looking, which we are going to solve. So I've talk about the so-called backward Cauchy problem. If we need to solve a sort of forward Cauchy problem, we will have a different stochastic equations, which will suit us later to construct the solution of the problem under consideration. Okay. Next, if we need certainly construction of a strong solution will lead to very severe assumptions concerning initial data and coefficients of the parabolic equation. And if we would like to make these conditions a bit more smooth, not so severe, we would probably try to construct a weak solution to parabolic equation, and this leads us to a new stochastic equation for, it will lead us to new stochastic equation for a stochastic process. And in fact, to explain what's written here, it's much more convenient to deal not with the itostochastic iter representation of the stochastic equation, but with the so-called Stoyanovich representation. And so Stoyanovich representation is just in the sense which it is used here. It's quite the same as ito, but we add a special drift which allows to our stochastic differential to be a vector field instead of usual ito stochastic differential. Okay, so if we will consider such an equation, and then we would like to add to it something like this, to construct the solution of a weak solution of the parabolic equation. But here the situation is not so much straightforward. In fact, we need not the solution of this equation, but we need to consider a stochastic flow generated by this equation. Then we need an inverse stochastic flow. We need a special equation to describe this inverse stochastic flow, and then we can really can add the closing relation, which makes our system to be closed and to be prepared to solve it. Okay, and so here we have this W hat is a Wiener process, but with time directed differently, comparing with delta WT. So, and the last, okay, let me mention that this approach, in fact, in a linear case was developed by Kunita, and we applied to semi-linear case, and so there are a paper of mine and our common paper with Wojcinski. And in fact, we have applied this approach to study Navier-Stokes system in joint work with Sergio Albaverio. So finally, this approach says us, okay, that if we want to construct a weak solution to weak in the sense of integral identity solution of this parabolic of this Cauchy problem, we have to consider the stochastic equation for a inverse stochastic flow to consider a system like this. But after that, when we manage to solve this system of equation, in fact, we need a very nice representation for the stochastic differential of inverse flow, which allow us really to prove that this function f will be a weak solution to the corresponding Cauchy problem. Okay, and finally, it's a bit long introduction, but finally we are going to discuss how to deal with nonlinear stochastic nonlinear parabolic equation of type 114, for which we would like to construct a viscous solution. Once again, it's a different notion for solution, and I have given here the definition of it, but we really will need it to prove that so we have to construct the solution of the equation for yt, and then try to check that yt, which will coincide with our function u t psi t will lead us to the solution of starting problem. Okay, let me tell a few words concerning the idea of proof in this simplest case in which, with which I have started. Because I will need this construction later to deal with fully nonlinear equations. So we need some assumptions concerning coefficients. They should be, they could grow in an, as, sorry?
May you go one slide?
Sure.
Please.
Before?
Yes.
Okay.
So I didn't really understand how you.
Okay.
How you get out of C and Y?
No.
In this.
In this case, so our we don't discuss now the U will be bounded really, and a bounded function U will be called the solution of the if for any function phi which is smooth, we will have these two sort of inequalities.
Okay. Okay. Okay.
It's a very special notion. And, sorry, I don't. Maybe I'll tell.
When the strong solution exists, then viscous, then it is viscous.
Yes, sure. Okay, so we have some conditions under which, in fact, we can prove that successful approximation to solution of this system will converge. But in fact, each time for this case, we need some to prove this a priori estimate. We certainly need some good inequalities. And so lemma 2 gives us the inequality like this. In particular, it shows that, in fact, we can precisely construct the majorizing function for our a priori estimate, and we can see what is the length of this small interval over which we can define our strong solution. And this interval depends on initial function and certainly on conditions on coefficients. Okay, next problem which we would like to discuss is not the scalar nonlinear Cauchy problem, but system of nonlinear parabolic equations and the discussion of the solution of the system of such equations. To this case, we need once again to construct the stochastic representation and stochastic. Yeah.
Sorry, I got lost in the previous part. So did you finish the previous part?
Yeah.
So what is the result?
No, I have not finished because what was stated in this theorem is that there exists an interval such that for this interval we have the solution of stochastic, yet only of stochastic problem. Then we have to prove that the solution of this function f, if we manage to prove that it is smooth enough, say C2, then it will be a classical solution to the Cauchy problem we have started with. Okay?
Still on this interval T1 between T1 and capital T.
Yeah. I told that this lemma just gives us the possibility to compute this interval. Okay.
So which information about the initial function or terminal function do you actually use in this estimate?
In this estimate, just boundedness and Lipschitz continuity. And later, certainly, let me Okay, in a few minutes I will tell what next we will need, because now we just only proved that to prove the solution of the stochastic equation, it's enough for us to have Lipschitz continuous coefficients of this. And so suppose that we have solved what we need, so it's enough that function u will be Lipschitz continuous. Okay. But to prove more smoothness of the solution, we certainly need more assumptions. But first, let me start with the discussion of the solution to system of nonlinear parabolic equations. To solve such a system, in fact, we have to consider a new system of stochastic equation. So we will have almost, we will have similar equation to 2.2 for the xi function, but we have a new equation 2.3 which describes a multiplicative linear functional. So it's a linear equation with coefficients depending on the underlying stochastic process. And then we consider the so this square is just a scalar product in this space RD1 where function belong to and values of function belong to. And so we have such a, once again, we have this closed system, which once again we have to solve first. And in this case, let me mention that in fact, we need we have to add some new assumptions concerning new coefficients, C small and C capital. And in fact, C capital, it's a coefficient which looks like, you know, the potential which was in Feynman-Katz formula classical. And C capital is add diffusion to this exponential. So in this, what is should be stressed in these estimates? So rho zero in the upper estimate for C small might be negative, and if it will be negative, it may allow us to enlarge the interval on which we are looking for solution. Okay, so then once again we need just to construct the solution of this nonlinear system. We need to linearize it and to prove a priori estimate similar to that lemma which I mentioned earlier. In this case, once again, we may construct precisely the majorizing function and the interval on which this majorizing function is bounded. Then we use this a priori estimate to prove, sorry, this should be the system of equation which we started with, this one, 2-1. Okay, so the theorem is that, now suppose that, let's come back to the, let's come back to initial scalar nonlinear parabolic equation. And let's mention that if we try to formally differentiate this equation, we will come to a system which will have structure precisely like this system 2-1. So if you will take for u, unfortunately once again both they are u, but if u will be the solution, f, okay, sorry, f was the solution of scalar equation, and we take for u the gradient of f, so we will have the system for gradient of f of precisely this type. And it means that if gradient of coefficients and gradients of initial data will satisfy the condition which we put on our coefficients for the system, it will lead us to proving that there exists both function itself and its gradient. And if we will make this procedure once again under suitable conditions, so we will prove that the function f, which was constructed in the first part, is a solution of, is a smooth solution and strong solution to the original parabolic system, parabolic equation. Okay. What interesting else may be discussed with relation to this system of equation is the following. Suppose that we have this system which has a small parameter, small diffusion, and we would like to see what will happen if the epsilon goes to 0. In this case, this represents in fact, it should be mentioned that we have, in this, when we have started to discuss, I didn't mention it at that time, that we have coefficients b capital in the system, and we have no coefficient b capital in our stochastic system. And that is simply because the relation which should be kept, and it's the relation looks like this. C capital is B capital is equal to C multiplied by A. So since this is the structure of the equation we are looking for, which is connected with the structure of stochastic representation, seems that if A will go to 0, so we will have not the system of parabolic equation, but, not the system of hyperbolic equation, but just the system dul dt plus c small u. But in general it's true, but we can found some situation when really we will have a sort of vanishing viscosity principle which leads us from the system of parabolic equation to the system of nonlinear hyperbolic equation. And so we assume that the matrices, so okay, for the simplicity, let's consider the case when X, our diffusion is one-dimensional. And in this case, we can prove that this equation, the system which corresponds to this stochastic system, which corresponds to the system of parabolic equation, looks like 2, 9, 2, 11. And so we see that epsilon, the corresponding, to preserve B, since A is epsilon A, so secondly we need that C capital have epsilon to the power minus 1. And in this case, something strange, it's difficult to prove that the existence of this equation. But once again, since we have choose some special conditions, in this special condition we can see such an interesting picture. The picture is like this. Secondly, the solution of our linear stochastic differential equation is just the exponential. This exponential is written here, and suppose that our alpha, these are eigenvectors of the matrix C alpha. And suppose the conditions were stated before, that this C alpha or B alpha, what is the same, since now A is simply a number or a scalar function. So we assume that the spectrum of this matrix is simple, and in this case we see that the structure of the eta alpha looks like the following.
Can Can you ask you, in this Feynman cards type representation, what is DW?
No, WT, it's a Wiener process each time.
Oh, it depends on tau.
On tau, yes.
Oh.
On T, by tau, there's no tau. Depends on T, yes.
Yeah, there is a tau. Integrate.
Where do you
Oh.
yeah, it's a parameter of integration, yes. Depends on tau, sure.
It's
Yeah,
W
yeah.
of tau.
Yeah, yes, yes. Okay. Under this assumption, then if we choose initial data of our for our eta, we choose for initial data the eigenfunction of eigenvector of the matrix C, then we will have the relation which is precisely reminds us about Girsanov theorem. And since once again it's just simply a scalar object here, so let's put it into our representation, and then we will see that what we have is the relation like this. And since at the right hand side of this angle bracket we have Girsanov formula, so we may change the measure and write it through the expectation with respect. Sorry, the expectation is omitted. The right hand side of this formula should be expectation R alpha U0 psi which sxt. Okay. And what is psi tilde? Psi tilde is just a stochastic equation which looks like what is written in the last line. So it means okay. It means actually that we can go to the limit epsilon goes to 0.
Yeah, I still don't understand. What is tau in this last equation?
Sorry, it should be t. There are some misprints in the formula. I'm sorry. Yeah.
Okay.
Every argument here is t. Okay. So, and the next topic, which I would like, I'm sorry, it's a sort of brief review of a number of problems which I've been interested for a long time, so I would like to discuss them. Now let me say a few words concerning quasi-linear equations in system. The case when coefficients of our parabolic equation depends not only on function u but on its gradient as well. To deal with this sort of equation, we have started to study this equation with Yuri Lvovich-Daletsky in the 80s, and then there are some papers of mine. So to study the solution to this equation, we have used such a procedure as differential prolongation. Once again, we formally differentiate the the original equation. Then we will have a system of equations for the original equation and its gradient, for the solution of original equation and its gradient. It comes to be that this system is a diagonal system, and it has precisely the same structure as the system which was a general system for us. And it means that, in fact, our aim, just for the moment, is to reduce this quasi-linear system to a semi-linear one. It means that I would like to obtain from the original scalar parabolic equation, from original scalar parabolic equation 3.2, I would like to obtain possibly a system of equation, but with coefficients depending only on the function u itself, not of its gradient or something else. One can manage to do it, but it's not enough to differentiate once. We have to differentiate the original equation twice. And nevertheless, we will obtain the new system with, once again, with structure of the system we have studied before. And that's why if we assume that coefficients of this new system, which are function of gradients of derivative of the coefficient of the original system and so on, which it's rather messy thing, but the structure of this messy thing is very strict. It's really, once again, a system which has diagonal principal part and non-diagonal first order and zero order terms. And so if we will do, in this way, we can consider not only a semi-linear but a fully nonlinear system as well. But this time we have to differentiate 3 times. And after 3 times differentiation, we will once again, we have a closed system of parabolic equation with coefficients depending only on this new function, which has 4 components. And so we have here blue, this is diagonal part, and all other terms depends only on the component of this new function. And what I would like to say is that it allows us to apply the whole procedure which has been discussed before, and apply the results of the previous theorems. And finally, let me say, if I have 10 minutes more, just to discuss what we can do with viscosity solution of these nonlinear PDEs. Let me mention that, in fact, the backward stochastic differential equations theory was started in the papers by Pardue and Peng in 19th of the last century, and it's very much developed till now. And a lot of works, but I have seen only one paper concerning which is connected with this fully nonlinear parabolic equation. This is a paper by Ceredito, Tuzi, 4 people, Victoire and Sonner, seems to me. Okay. But here we suggest a different approach to construct the solution of the viscous solution of this equation. So the approach I would like to suggest is a bit combination of the approach which was discussed previously and the approach of viscous solution. So in spite of looking immediately for the solution of 4.1, I would like to differentiate it once again, but this time I don't need to reduce to a system which depends only on new function u itself. It's enough for me that coefficients would depend on the function u and its gradient. So this time it's enough for me to differentiate only once, and then I will have the new system 4.5, which is mostly of the form of the system which had been studied in a number of works connected with backward stochastic differential equation. The only, the only peculiarity, usually people working with backward stochastic differential equation start with a simple equation for the underlying process psi, which usually even not connected with, which evolves separately. And then look for the solution of the corresponding backward stochastic differential equation. So backward stochastic differential equation here is the equation from 4.7 and 4.8, and they are backward because we solve them with initial data on the right-hand side of time interval. Okay, and but we need here a different approach. So we need the stochastic differential equation with coefficients depending on the function y on p and q, and we have to solve this new system and to construct the solution of this system. It could be done by, once again, by a sort of successive approximation system sequence, and using this martingale representation, which is usual to construct the solution of backward stochastic differential equations. Okay. So suppose that we have constructed this y capital T. We have to prove that this that its first component, which was called I don't remember how I call it, y, yeah, u. Sorry. We have two-component object here, v capital, which is u, and v small. So we have to prove that u small is a solution, is a viscosity solution of our starting parabolic equation. But since we have reached the situation when the process y is a solution of the backward stochastic equation of a general type, which was rather thoroughly investigated in various papers. So we can use a general approach to construct, to prove that this pair of stochastic processes define the solution of the original fully nonlinear parabolic equation, and the proof of this is tightly connected with the definition of the viscous solution, which has been done. Remember that it was told that we can prove that U is a viscous solution if for any smooth function phi we can prove the inequality, instead of initial equality we will obtain the inequality. And this is proved using, this fact is proved using eta formula, and in fact it seems that I have no time to point out very precisely how it's done. If there will be questions, I will tell. Maybe just to finish my talk, okay, there is a number of references to the topics which have been discussed during the talk, and let me finally mention only two things. The application of the whole this theory, first to the Navier-Stokes system. I would like to show what how looks like the corresponding stochastic problem. So if we will start with Navier-Stokes system, and in fact change the condition divergence u equal to 0 for another relation which is equivalent, that nabla p, where p is pressure, is equal to trace of the square, okay, of the gradient of u, we can reduce this system to a stochastic system which looks like 5.3, 5.4, 5.5. We can solve this under this representation will lead us to on a very small interval, lead us to a smooth solution of Navier-Stokes system. But if we will deal with this stochastic flow, which I have spoke before, and we will construct a new system which looks like 5.6, 5.8, then we can construct a weak solution to this system. Okay, and finally, let me mention that one more source of problems, it was interesting for me, but for me comes to be a financial mathematics. So, since I have been to do, at least to teach students financial mathematics, it appears that in this field there arise fully nonlinear parabolic equations as well. If you are dealing with a market which is illiquid, or you have to take into account transaction costs, it will it will have effect to your trading to how you have to trade, and if you, in this case, if you would like to derive the arbitrage-free price, the equation which would describe the arbitrage-free price of a certain derivative with a contract function phi capital, then it will lead you to a fully nonlinear parabolic equation like this, and you have to study it probably using all the machinery which has been discussed in this paper. Okay, thank you very much.
You have to make sure that you will be trading on some small time interval.
Yes, yes. By the way, up to my mind, it shows that in such a complicated markets, you always have, you know, blow up. In a sense, you can't avoid it. If the system is complicated, it can't, you know, stand forever. Okay.
Yes, question.
Yeah, you discussed very, very general equations.
Yeah.
A lot of equations. Yeah. I have such question. What you can show for physical workers? I mean, let us consider just reaction diffusion equation. Yeah?
Okay.
And this heat equation with polynomial nonlinear.
Yeah. Yeah.
What is the algorithm? What I should do to produce representation?
Okay.
In this simplest.
Yeah. Yeah. Okay. So you have this equation.
Yeah.
Okay.
And I consider Cauchy problem, and I don't understand why plus Laplacian.
For me, for the moment, it's easier because I would like to deal with backward.
Okay.
Not to think. Certainly, I can do it.
Yeah.
Okay. And so you have to write the equation which will be this time. Okay, let's put at least sigma square here, okay? This will be this one, but after that you will have usx equal to exponential of integral from s to t capital f u tau ditto, U0, WT. This one. Okay, so x psi s is equal s, and since now it's everything.
But what is in representation? I have function.
Sure, you have to after that you have to solve this. You reduce your parabolic equation to the solution of integral equations.
And it gives me something for computation or really representation for solution, because it is just again another equation.
Yes,
In
but this time not differential one, but integral one, and that's why you can you have to apply successive approximations and write here n plus 1 and here n. Okay.
Yeah.
You mean one act exponential.
And probably even. Let me see. Okay. Yes. Okay. Here you have to. It's.
In the right hand, it's one less. In the right hand side, the index one less.
Yes, exactly. But let me see if it's yes. Yeah. Okay. Yeah. Exactly. And we don't really, since psi is simple thing, we don't.
But this stochastic equation,
And-
integral equation,
Yeah. It's
will
an
it have
integral-
solutions? Will it have solutions only locally
Yes.
or globally?
It depends on the function f.
How you can you check existence
I-
of some function from this representation?
Yeah. Once again, I will. In fact, in my case, there was written in this way. Okay.
Right. Okay.
Yeah.
Fine.
And so, if you you see, you might be. I put there rho 0, which I told you that might be negative, okay?
Right.
And plus rho 1. You multiplied, okay, by p, I don't know. If you will play on these coefficients, it,
P of u equal 1 minus u, u minus 1 will be classical.
yeah,
Fisher-Kolmogorov.
yes. Yeah.
And you can check in this situation convergence,
Yes.
existence of solution. But typically solutions should be not unique.
Not here.
Maybe.
Not here. They might be.
But will you be able, for example, for this case that Yuri mentioned, to prove it on the whole axis, time axis, globally?
Global axis.
Certainly, here the situation is not so simple, because this equation can. I've been interested in a smooth solution of the equation which discussed. In this equation, you can have, this moving.
Moving wave, but moving
Yes.
wave is also.
Yeah.
Explosions.
Yes.
Why not?
And this equation was studied well enough by Friedlin in his book, and so I've been interested in a bit different things. But okay.
Actually, we have not representation of solution.
No,
in
we
stochastic.
have a reduction.
Yeah,
Yeah, we have a sort of yes. Representation.
Formula which gives us
Representation means that you have explicit solution to.
But you don't have.
No, sure, certainly not. Certainly not. It would be too. too much.
Any other questions? Okay, let's thank the